In this video, we're going to talk about monotonic sequences and bounded sequences. So let's begin our discussion with monotonic sequences. A monotonic sequence is a sequence that is always moving in one direction. It can be an increase in sequence, or it could be a decrease in sequence. To show that it's always increasing, you need to show that the first term is less than or equal to the second term, or you could say the second term is greater than or equal to the first, and the third term is going to be greater than or equal to the second, and so forth. You could also show that the first term divided by the second term is less than or equal to 1. So that's a monotonic increase in sequence. And to show that the sequence is always decreasing over time, you can use this. A sub 1 has to be greater than or equal to A sub 2. And the second term has to be greater than or equal to the third term. Or the third term has to be less than or equal to the second. And so forth. And so, if you focus on this part of the inequality, where A1 is greater than or equal to A2, if you divide both sides by A2, you'll get this expression. A1 divided by A2 is greater than or equal to 1. So there's different ways you could show that this is a monotonic decrease in sequence, and this is a monotonic increase in sequence. Now let's draw a graphical representation of an increasing monotonic sequence. So here you can see the terms in a sequence, they're always going up. So that's an increase in monotonic sequence. And here's an example of a decrease in monotonic sequence. Now what about this sequence? Would you say it's a monotonic sequence? Notice that there's no general trend. It's not going up or down. It's actually doing both. It goes up, down, down. So the long-term trend is it's basically just staying around that midline. And so it's not increasing in the long term or decreasing in the long term. So therefore, this sequence is not monotonic. Now let's work on an example problem. Consider the sequence a sub n is equal to 3n divided by n plus 2. So is this a monotonic sequence? And if it is it always increasing or decreasing? Well, first, let's get a general feel for the sequence by listing out the first 4 terms. So the first term, a sub 1, it's going to be 3 times 1 divided by 1 plus 2. So that's 3 divided by 3, which is 1. So I'm going to write that here. First term is 1. Now the second term, that's going to be 3 times 2 over 2 plus 2. So that's 6 over 4, which we can reduce that to 3 over 2. Now the third term, that's going to be 3 times 3 over 3 plus 2. So that's going to be 9 over 5. And the fourth term, 3 times 4 divided by 4 plus 2. So that's 12 over 6, which is 2. Now let's get the decimal values of all the fractions for those terms. So 3 over 2, that's 1.5, and 9 divided by 5, that's 1.8. So we have a monotonic sequence. We could see that it's always increasing. Now how can we prove that it's always increasing instead of just plugging in the numbers? Well, we need to show that the second term is greater than the first term. But we need a generalized way of doing that. So we need to show that a sub n is less than or equal to the next term, which will be a sub n plus 1. So if we can show that this statement is true, then we could show that every other term, it's going to be increasing. So we can also show that a sub 2 is less than a sub 3, a sub 3 is less than a sub 4, and so forth. So let's go ahead and replace a sub n with 3n over n plus 2. Now, if that's a sub n, what is a sub n plus 1? So everywhere we see an n, replace it with n plus 1. So this is going to be 3 times n plus 1 divided by n plus 1 and then plus 2. So all we need to do is show that this inequality is true. If it is true, that means that the original inequality is true. And that's how we can show we have an increase in monotonic sequence. So first, let's simplify the expression. On the left, we have 3n over n plus 2. On the right side, I'm going to distribute the 3. So it's going to be 3n plus 3. And then on the bottom, I'm going to add 1 plus 2, which is 3. So that's just going to be n plus 3. Now, what we're going to do is cross multiply, which is equivalent to first multiplying both sides by n plus 3. So then on the right side, these will cancel, and then multiplying both sides by n plus 2. So on the left side, these will cancel. So we're going to have 3n times n plus 3, and that's going to be less than or equal to 3n plus 3 times n plus 2. Now let's go ahead and distribute the 3n to n plus 3. So 3n times n, that's going to be 3n squared, and then 3n times 3, that's 9n. And then on the right side, we have 3n times n, so that's 3n squared, and then 3n times 2, so that's 6n, and then 3 times n, 3n, and then 3 times 2, which is 6. So subtracting both sides by 3n squared, we can eliminate this term. And so we have 9n, which is less than or equal to 6n plus 3n, that's 9n. And then if we subtract both sides by 9n, we're going to have 0 is less than or equal to 6. Now, is that a true statement? Is 0 less than 6? Yes, it is. So because this statement is true, the original statement that we started with, which was a sub n is less than or equal to a sub n plus 1, well, that's also a true statement. And that's how we can prove that we have an increase in monotonic sequence. Now let's work on another example. So let's say we have the sequence a sub n is equal to 3 over 4 raised to the n power. So is this a monotonic sequence? And if it is it increasing or decreasing? Well, let's make a list of the first 4 terms just to see what's going on. So the first term, a sub 1, that's just going to be 3 over 4. The next term, when n is 2, 3 squared is 9, 4 squared is 16. And then the third term, when n is 3, 3 to the third power is 27, 4 to the third is 64. And then for the fourth term, 3 to the fourth power is 81, 4 to the fourth power is 256. Now let's get the decimal values for these fractions. So 3 over 4 is basically 0.75. 9 over 16, that's 0.5625. 27 over 64, I'm going to start rounding these, so that's like 0.4219 approximately. And then 81 over 256 is approximately 0.3164. So we can see that the numbers are getting smaller and smaller and smaller. So the first term is greater than the second term, or the second term is less than the first term. So this appears to be a decrease in monotonic sequence. Now how can we show it? So we need to show that a sub n is greater than or equal to the second term, or the next term, a sub n plus 1. Now in this case, I'm going to divide both sides by this term, a sub n plus 1. So a over n, not a over n, but a sub n divided by a sub n plus 1, that has to be greater than or equal to 1 to show that this is a decrease in monotonic sequence. Now, let's go ahead and replace a sub n with 3 over 4 raised to the n power. And then let's replace a sub n plus 1 with 3 over 4 raised to the n plus 1. Now let's show that this is greater than or equal to 1. Feel free to pause the video and try it. So what do you recommend that we do in order to show that it's greater than or equal to 1? We need to split this into two parts. So 3 over 4 raised to the n plus 1, we can write it as 3 over 4 raised to the n times 3 over 4 raised to the first power. Because when you multiply by two common bases, you can add the exponents. N plus 1 is equal to that. So now, in this form, we could cancel 3 over 4 raised to the n power. And so we're left with 1 divided by 3 over 4. And let's show that it's greater than 1. So we're going to multiply both sides, the top and the bottom, by 4 over 3. 4 over 3 times 3 over 4, that's 1. The 4's cancel, and the 3's cancel. So all we have left over is that 4 over 3 is greater than or equal to 1. Is that a true statement? Yes, it is. 4 over 3 is about 1.3 repeating, and that's greater than 1. So therefore, our original statement, that is a sub n is greater than or equal to a sub n plus 1, that is a true statement. So this proves that we have a decreasing monotonic sequence. Now let's talk about bounded sequences. So let's say that the sequence a sub n is less than or equal to some value, which we'll call capital N. If that's the case, then we say that the sequence is bounded above, which means that it has an upper bound or a ceiling. So to represent that graphically, let's say we have an increasing sequence, but it never goes higher than this line. So we say the sequence is bounded above. It has an upper bound at m. So it has a ceiling, so to speak. Now the second case, the sequence can be bounded below. It can be greater than or equal to n. So in this case, it has a floor. So let's call it capital N. And let's say we have a decreasing function. So as you can see, it never goes below n. So we say that the sequence is bounded below, meaning that it has a lower bound or a floor at end. Now let's say that the sequence is between n and m. In this case, we simply say the sequence is bounded. So if the sequence is bounded above at m and bounded below at n, then the sequence is simply bounded. So let's say this is a sequence. It's an oscillating sequence. So looking at this picture, we could see that it's bounded above at m, and at the same time it's bounded below at n. So that's just a bounded sequence. It has an upper bound at m and a lower bound at n. Now this leads to an important conclusion. That is, if the sequence a sub n is bounded, where it's bounded above and bounded below, and it's monotonic, it can be always increasing or always decreasing, then the sequence converges. So if it's bounded and monotonic, the sequence converges. So let's see if we can use an example to illustrate this. Consider the sequence a sub n is equal to 1 divided by n squared. So is this sequence convergent? Is it monotonic and is it bounded? Well, let's find out. Let's begin by writing the first four terms. So a sub 1, that's 1 over 1 squared, which is 1. A sub 2, 1 divided by 2 squared, so that's 1 over 4. A sub 3, 1 over 3 squared, so that's 1 over 9. And the next one is going to be 1 over 16. So looking at these numbers, this appears to be a decrease in monotonic sequence. But now we need to prove it. So one way we can illustrate that it's a decreasing function is if we graph the corresponding function 1 divided by x squared. And so this graph is going to look like this on the right side, where x is greater than 0. And so that appears to be a function that is always decreasing. Another way is also to take the first derivative of this function, f prime of x. F of x, if you rewrite it, that's x to the negative 2. So then, using the power rule, that's going to be negative 2x to the minus 3, which is negative 2 over x cubed. So when x is greater than 0, the first derivative is always negative. Now, if f prime is negative, that means that the function f of x is decreasing. So that's another way to determine if the sequence is decreasing. So if you write the corresponding function that's continuous and determine the sign of the first derivative, if it's negative, then the sequence will be decreasing. If it's positive, then that tells you the sequence is increasing. Now, another way to show that we have a decrease in monotonic sequence is to show that a sub n is greater than a sub n plus 1. So for instance, we want to show that a1 is greater than or equal to a2. So the previous term is going to be larger than the next term. Now a sub n, we know it's 1 over n squared. And a sub n plus 1, that's 1 over n plus 1 squared. So let's cross multiply. So we're going to have n plus 1 squared is greater than or equal to n squared. So now we need to FOIL n plus 1. So we need to multiply it by itself. If we do that, we're going to get n squared plus 2n plus 1, and that's greater than or equal to n squared. Subtracting both sides by n squared, we will be left with 2n plus 1 is greater than or equal to 0. So for n is equal to or greater than 1, this statement, is it true or false? So if we plug in 1 for n, 2 times 1 plus 1 is 3. 3 is greater than 0, so that's true. If n is 2, 2 times 2 plus 1 is 5. 5 is greater than 0. So this is always true whenever n is equal to or greater than 1. So that's another way you can prove that you have a decreasing monotonic sequence. So now that we've established that we do have a monotonic sequence, we need to determine if this sequence is bounded. Does it have a ceiling and a floor? Well, let's find out. So if we were to graph the sequence, the first term, where n is 1, would have a y value of 1. A sub 1 is 1. The second term is going to be 1 over 4, which is probably going to be somewhere over here, and then 1 over 9, and then 1 over 16, and so forth. So because it's a decreasing function, the first term is going to be the highest. So therefore, it's bounded above at 1. Now, is it bounded below somewhere? A sub n, which is 1 over n squared, that's always going to be positive. Anytime you square something, you're going to get a positive result. And so, whenever you have a function that is always positive, the lowest value that it can ever be will be 0. So we could say that it's going to be bounded below at 0. It never really touches 0, but it's going to get close to 0. So we have a sequence that's bounded below at n and bounded above at m, so it's simply bounded. So now that we've established that the sequence is both bounded and monotonic, we can make the statement that this sequence is convergent. Now, another way in which we could establish convergence is to determine the limit as n approaches infinity for the sequence a sub n. If it equals some value L, some constant, then we know the sequence converges. If it doesn't exist, or if it goes to positive or negative infinity, then the sequence diverges. So what is the limit as n approaches infinity for the sequence 1 over n squared? So 1 divided by a very large number is going to be approximately 0. So we could say that the limit is equal to 0. So because it's equal to a constant, the sequence converges. Now let's look at another example, and that is sine n. So determine if the sequence is monotonic and if it's bounded, and at the same time determine if it's convergent. So let's graph the corresponding function sine x. Sine x is an oscillating function that looks like this. And so it varies between 1 and -1. So therefore, we could say it's bounded below at -1 and bounded above at 1. So therefore, this particular sequence, the corresponding sequence being sine n, we could say it's a bounded sequence. Now, is it monotonic? Well, it increases, then decreases, then increases. So it doesn't always increase or always decrease. There's no general trend. So it's not monotonic. So therefore, since it's not monotonic, but bounded, it's divergent. In order for the sequence to be convergent, it has to be both bounded and monotonic. Now let's work on one last example. So consider the sequence a sub n, which is 3 to the nth power divided by n factorial. So is the sequence convergent or divergent? What would you say? Well, a quick test is to take the limit as n approaches infinity. So what is the answer to this question? Now for this type of problem, it might be difficult to evaluate the limit. And so this method may not be the best method to attack this problem, because if you have a free response test, it's not going to be easy to evaluate the limit. Now granted, you can always plug in numbers and see what's happening as n increases, just to get a good idea if it's going to be convergent or divergent. So let's say if n is 10. So 3 to the 10th power divided by 10 factorial, if you plug that into your calculator, you should get 0.01627. Now let's say if we increase n from 10 to 20. This is going to be a very small number. It's going to be approximately 1.43 times 10 to the -9, which is approximately 0. So we could say that as n approaches infinity, the sequence, it reaches 0. So therefore, this indicates that we have a convergent sequence. But now let's prove that it's convergent by showing that it's monotonic and also it's bounded. So let's begin by establishing if it's increasing or decreasing. So let's write out the first 5 or 6 terms. So let's start with a sub 1. That's 3 to the first power divided by 1 factorial, so that's just going to be 3. Now a sub 2, that's going to be 3 squared over 2 factorial. So 3 times 3 is 9. 2 factorial is 2 times 1. 9 over 2 as a decimal, that's 4.5. Now a sub 3, that's going to be 3 to the third power, which is 3 times 3 times 3. And then 3 factorial is 3 times 2 times 1. So we can cancel 3, And once again, it's 9 over 2, which is 4.5. Now let's move on to the fourth term. So 3 to the fourth power over 4 factorial. So we're going to multiply 4 3's, and 4 factorial is 4 times 3 times 2 times 1. So this becomes 27 over 8. And 27 over 8 as a decimal, that's about 3.375. Now looking at the fifth term, so that's 3 to the fifth over 5 factorial. I'm just going to type that one in. And so that's 81 over 40, which is 2.025. And then let's do one more. So 3 to the 6 over 6 factorial. That's 81 over 80, which is 1.0125. And we know that the 10th term was 0.01627. And so notice that initially the sequence increases. And then starting from the second term, it begins to decrease towards 0. So would you say that this is a monotonic sequence? Yes, it is. Even though it goes up initially, what is the long-term trend? The long-term trend is that it's decreasing over time. So starting from the second term, it's always decreasing. So this is a decreasing monotonic sequence. Now, let's confirm it using a more generalized approach. So we know that a sub n has to be greater than or equal to a sub n plus 1 in order for us to have a decreasing monotonic sequence. So the previous term has to be larger than the next term. So dividing both sides by a sub n plus 1, we're going to get this expression. So this is going to be 3 to the nth power divided by n factorial divided by 3 to the n plus 1 over n plus 1 factorial. So let's show that this is greater than or equal to 1. So let's use the keep, change, flip principle to write it like this. Now, n plus 1 factorial, that's going to be n plus 1 times the next term, which is, you got to subtract this by 1. So that's just going to be n factorial. And 3 to the n plus 1 is 3 to the n times 3 to the 1. So we can cancel 3 to the n, and we can also cancel n factorial. And so what we have now is that n plus 1 over 3 is greater than or equal to 1. Now let's solve for n. Let's multiply both sides by 3. And so we'll have that n plus 1 is greater than or equal to 3. Subtracting both sides by 1, we'll have n is greater than or equal to 2. So now let's think about what this means. So we started with this expression for decreasing monotonic functions. So this means that the function is decreasing, not the function, but the sequence is a decreasing sequence only when n is greater than or equal to 2. And that is true. Starting from the second term, we could see that it's always decreasing. And so let's say if we were to graph this function, let's say this is 1, 2, 3, 4, and 5. So when n is 1, the first term will have a value of 3, the second will be at 4.5, the third is at 4.5, and then it's just above 3, and then it's down to 2, and then 1, and then it's just going to keep decreasing towards 0. So even though it goes up initially, starting from the second term, the long-term trend is that it's decreasing over time, which means we do have a decrease in monotonic sequence starting from n is equal to or greater than 2. It's always decreasing starting from the second term. Now, because it's always decreasing at this point, that means that this is the highest value. So it's bounded above at 4.5, and because this is always positive, it's bounded below at 0. So we do have a bounded sequence. We have an upper bound at 4.5 and a lower bound at 0. So because it's bounded and it's monotonic, we can therefore say that this sequence is convergent. And as we saw, if we take the limit as n approaches infinity, it converges to 0. So the graph, you can see that it's approaching the x-axis. So this is a convergent sequence.